Hi, this is Dr. Harrington, and we are now going to investigate numerical differentiation. So, here's the thing I want you to notice about numerical differentiation. It's just like from Calc 1. You're going to see that we're going to have a curve. We'll call this, say, y is equal to f of x. And I can put 2 points down, say here, and this is what I want to know where the derivative is at, say at x naught. And so then I'll just move over a little bit and call this one x naught plus h. And if I draw a line, that's what we call our secant line. And as we allow h to go to 0, we are going to get our tangent line, which our tangent line would look somewhere over here. That's going to be our tangent line. So that will be our tangent line. That's what we want to get ultimately. Now the question is not how to take the derivative, because we know that. We've been doing that for a long time. But the question is, first of all, what is the error bounds for these things? And, is this practical to use? So let's take a consideration. So let's consider the Taylor series, t of x. Now this is going to go on forever, and I'm going to use, just to be clear, I'll be doing the Taylor series for f of x at x naught. So this is going to be equal to f of x naught plus the derivative f of x naught times x minus x naught plus 1/2 f double prime of x naught times x minus x naught squared plus ... Now this goes on forever, and that's the entire Taylor series for f of x. Now if you just look at this for a little bit, you'll realize that the derivative is here. And remember, we've already studied error bounds for Taylor series. And see, that's why I wanted to write it as a Taylor series. So now, I want to note that in our case, the Taylor series equals f of x precisely, and for this I'm going to need the remainder term to make that equal, So that's going to be f of x naught plus f prime of x naught times x minus x naught plus 1/2 f double prime psi times x minus x naught squared. Nice. And keep your eye on the prize. This is exactly what we want. Okay. So let's take a look. And again, I want to note here that this error bound, we're going to have that psi lives between, say, x naught and x1, say the next point. And I don't know which one's bigger, x naught or x1. That's why I didn't put parentheses, because I didn't know exactly which one was largest. So let's go ahead and write this out, the next step. So now we have that f of x is going to be equal to f of x naught plus f prime of x naught times x minus x naught plus 1/2 f double prime of psi times x minus x naught squared. All right. What I'm going to do now is, from right here, I'm going to replace that x with at just x naught plus h. So I'm going to have f of x naught plus h is equal to f of x naught plus f prime of x naught times x naught plus h minus x naught. And you'll see right off the bat that the x naughts cancel, which is pretty nice. And now I'm going to have plus 1/2 f double prime of psi, and I'm going to have x plus x naught plus h minus x naught squared. And just like in the other case, the x naughts cancel. So if I simplify this, I'm going to have f of x naught plus h is equal to f of x naught plus f prime of x naught times h plus 1/2 of f double prime psi times h squared. All right, now if I want to solve for this, let's take a look to see how this happens. If I want to solve this, then I keep that on this side and I bring everything over to the other side. So if I bring everything else to the other side, let's see. So I'm going to take this, bring that over. I'll take this, bring that over, and then I'll divide by h. So I'm going to have f of x naught plus h minus f of x naught, and then minus 1/2 of f double prime. Oh, I almost forgot this little, nope, that's perfect. I thought I made a little mistake, but I didn't. That's very rare. H squared, and then the whole thing divided by h. And that is going to equal to our f prime of x naught. Now let's see if we can simplify this a little bit. We're going to have f of x naught plus h minus f of x naught divided by h minus 1/2. And you'll notice that in this last term here, there's an extra h. So let me point that out to you. You'll see that you actually have, oh yeah, I still have the Vader symbol on there, I forgot. So you'll see that you have h squared, and when I divide by h, that just goes away. So the error bound is a little bit different than what you might expect, but it's 1/2 f double prime of psi, and it's just h. All right, so just to recap real quick, here's what you see. If I want to approximate this guy, the derivative of x naught, then I will do the difference just like we did in Calc 1, but this will be our error bound. So this is our actual error bound. And also note, I should put this over here on the side, that note we have different ways of calling these things. So if h is bigger than 0, then we call this a forward difference. Whoops, let me make that look better. That's 0. Then that's called a forward difference, because we're going forward, just like here in the picture. So if you go back and you look at this original picture, here we have x naught, and we're going to x naught plus h. This kind of comes back. Then you get what's called a forward difference. But you can do it in the opposite direction too, and that's just called a backwards difference. So if the h is less than 0, then you get a backwards difference. Whoops, that's hard to read. Backwards. Backward difference. All right, I'll do an example next. Thanks.